But let's do the simulation lecture quickly. This is something that I normally do earlier, but I deferred it until now. But I think it's useful to understand how to do simulations. And some of you mentioned that you haven't done simulations, but it's good to know this, I think. So basically, I think of this as how do you evaluate new ideas for new memory architectures? Something doesn't even exist yet. How do you actually study it, right? And the answer is usually simulation. But that's not the only answer, actually. Basically, it's really about evaluation in the end. How do we assess an idea will improve a target metric X? That's the more general question. And there are a variety of evaluation methods that are available to you as a computing researcher. One is theoretical proof. This is usually out of the question for computer architecture because we're really designing these systems, and it's usually you cannot prove something about these unless you're limiting your assumptions. And also, target metric X is a difficult proof, right? You can prove some security guarantees potentially, but performance is a bit tougher because you very much depend on the workloads actually in this case. The other is analytical modeling and estimation. This is actually very interesting, and it may be actually good to do this, but you need to develop some understanding of the system first to be able to do this. Simulation, as a result, is very useful in general, but this also has varying degrees of abstraction and accuracy, as we will talk about, because there are many types of simulation methods. Or prototyping with a real system, with FPGAs. I think this is also important, but of course it depends on the idea, right? What you can prototype. It's not always possible, for example, to prototype an emerging technology with FPGAs, right? A phase change memory with FPGAs. Good luck with that, right? You're not going to be able to do that. Processing in memory with FPGAs, maybe it's more possible with a limited way, but again, you cannot do it at large scale, right? You cannot see the large scale benefits of that. Or real implementation, right? Okay, I'm going to research phase change memory and how it's going to change the world, or flash memory 30 years ago. You go and really implement it. Well, that may be tough also, right? Because that requires a lot of resources, especially if you, if there are many, many design choices. This is very, very costly in general. And also the progress may be very slow over here because especially if you're changing hardware, which is really the subject here, the real implementations are very hard. So we could, for example, go and implement mbit in DRAM, but that's very difficult actually, it turns out, because nobody actually in academia can implement mbit. And if you actually think about the bigger picture, there are only 3 DRAM manufacturers, and there's a good reason for it, because this technology is very difficult to begin with. So we actually work with DRAM manufacturers to try to get it into the products, but you cannot do it without doing the other stuff, right? You need to get to a real implementation position first, and how do you do that? Okay, basically I think my point is there's a difficulty in architectural evaluation, and that usually, the answer is usually workload dependent. Remember the rat holes? The first rat hole is workload, right? You don't test that workload. The answer is usually workload dependent, and that actually leads to a lot of issues in general. Like think caching, for example. If you're, even something as simple as caching is very much workload dependent. If you're doing random access, your caches are useless. If you're doing streaming access, your caches, again, could be useless. If you're doing a lot of streaming data, you need to have some sort of locality, right? Or pipelining, again, or any idea we talked about, RAID or memory scheduling. And workloads change. They don't stay constant. And if you're trying to enable an idea 10 years from now, how do you predict what workload? So you need to actually operate at a more fundamental level sometimes, right? It's 10 years is so far that workloads may be completely different. And system also has many design choices and parameters, right? So an architect needs to decide many ideas and many parameters for a design. It's not a single thing. So it's really not easy to evaluate all possible combinations. Certainly not easy to implement all possible combinations in real life. And system parameters can also change while you're changing. Let's assume that you're designing a processor. Your system may be also changing, right? You're designing this processor. Today, processor design cycles are 4 to 5 years. Some accelerators take shorter, maybe 1 to 2 years, maybe less. GPUs used to be rolled out every 6 months or so, although maybe the changes were not that large, right, every 6 months. So you really need to race against the clock while everything is changing. And simulation is an enabler, I think. It really enables you to dream of the future. I think that's why I call it the field of dreams. But of course, there's a difference between dreaming and reality. So an architect, in my opinion, is a part of a dreamer, a creator. You dream of the future and you try to enable it. And I think simulation is a key tool to enable these dreams. Like many of you probably watched The Matrix, right? That's about simulation, I think, in general. Maybe that's my view of The Matrix, but how many people watch The Matrix? Okay. Not everybody. Okay, you should watch it if you haven't watched it. Essentially, simulation enables, I think the key thing simulation enables is the exploration of many dreams and how they compare against each other. You can do it very fast, assuming you're an expert in simulation. That's why I think that's really important. Because clearly you're not going to be able to do this if you try to implement every single idea that you have. You have limited resources, you have limited life. Even if you have unlimited money, you're not going to have enough time to explore many of the dreams. But you can do that with simulation. It enables a reality check of the dreams also, because you may be dreaming and you claim this many benefits, and you go in and simulate it in a good way, and then the simulator can maybe it tells you that, okay, this is a false dream, right? It helps you to decide which dream is better, like what are the alternatives better. Do you do processing in memory? Do you do monolithic 3D integration? Do you do both of them at the same time? There are many, many options that you can evaluate if you have a good simulator and if you're an expert in this, actually. Of course, it also enables the ability to fool yourself with false dreams, right? Meaning that if you didn't do a good job with your simulation, you may come up with an answer that's completely detached from reality. So that's why this needs to be, that's partly why I said this is really an art. And I think simulation makes the art even more art, let's say. So you need to have some understanding or an experience to be able to do the simulation. And I think this is really important because I don't see any other way than simulation to really explore many, many dreams at the same time. You could argue analytical modeling is another one. Yes, I agree with that actually. Analytical modeling is another one, but there's a danger in analytical modeling also because somehow you need to ground it. It's easier to ground simulation. It's harder to ground analytical modeling, I think. Okay, so why do we want high-level simulation? So there's also a spectrum of simulation, high-level versus low-level. RTL is basically register transfer level, gate level. You're very close to hardware in gate-level simulation, but it's very intractable for design space exploration. So if you want to actually, for example, look at your cache size and how it affects your workloads, RTL simulation is basically too slow because you're really essentially executing your workload on these gates that you've designed and that you're really simulating. It's too consuming, basically, especially over a large number of workloads for a long time, especially if you want to predict the performance of a good chunk of a workload. That's how big of a workload that you evaluate on a particular design. Usually RTL simulation of 10,000 instructions even could take a day, actually, depending on how big of an RTL that you're looking at. And especially if you want to consider many design choices. So the complexity is actually a lot. Workloads, what fraction of the workload, and how many design choices you're trying to consider. And this is an example from caching, for example. Cache size, associativity, block size, algorithms. You can easily have 1 million design choices, actually. Combination of those, if you're trying to just look at the size of the cache itself. And you have many caches in the system and many, many other components. Memory control and scheduling algorithms, we looked at some of them very briefly. In order versus out of order execution, all of these things within out of order execution, ... If you combine all of these, you have easily a huge state space exploration, explosion. So basically, the goal is to explore design choices quickly to see their impact on the workloads we're designing the platform for. And RTL simulation is not going to work very well. And there are different goals in simulation also, I must say. So if you want to do design space exploration, you really need high-level simulation. And if you're really good, you should do analytical modeling also, and you should calibrate the simulator with an analytical model, and both of them at the same time somehow. Of course, you cannot calibrate. Sometimes an analytical model could be better also, but we have another slide related to this. If your simulator is not good enough, for example. So we want to. So this is one goal: exploring the design space quickly and see what you want to potentially implement in the next generation platform. That's one goal, right? Another goal that's different from this sub-bullet is still explore the design space quickly and see what you want to propose as the next big idea to advance the state of the art. Here, the goal is really implementation of the next generation platform, not forward-looking as much. The second one is very forward-looking. Right? And your approach may be different in these simulators, actually, when you design these simulators. The second one may require much faster simulation, maybe less accurate simulation, but you can explore the design space much faster. But in both cases, the goal is mainly to see the relative effects of the design decisions. Basically, you're not really as much concerned about, okay, is the real performance matching the simulator perfectly? Right? You're more concerned about, I have a mechanism X and mechanism Y. Which one is going to be better for me to implement? And I have some threshold, of course, in terms of the performance delta that they should provide. And I think we'll need to leave soon, so I'll go through this relatively fast. Somebody was looking here. Okay, so yeah, but basically you want to look at the relative effects of design decisions. Okay, that's one goal in simulation. But another goal that's completely different is this: match the behavior of an existing system. Basically, we already have an existing system implemented, and you're designing a simulator for it. Now, your goal could be to match the behavior of that system in the simulator so that you can debug and verify it at cycle level accuracy. Right? Why is this useful? Well, this is useful because if you match that system, now you can actually simulate and figure out what quick fixes that you can make to that system so that you can make it better in some way. This is done by companies a lot, actually. Like Intel designs a processor X, and they have a simulator X for it. And for some reason, the processor X is not working well, and they fix something in the simulator, and they see if that actually improves the processor, and they make that fix in the processor quickly. Yeah, that's what I said over here. Propose small tweaks to the design that can make a difference in performance or energy or some other metric. In this case, your goal is really high accuracy. It's a completely different goal from here. Here, you want to be really accurate. And actually, there are people, really experts, who spend time in these companies that I know of personally who are very dedicated. Their goal is to really bridge the gap between the simulation and real hardware. And the simulator is very low level in this case, very sophisticated, very hard to change in some way. And they try to make it match. Usually the error rates are maybe 0.5%. If you get to 0.5%, you're lucky, actually. I haven't seen a perfect simulator yet. That's zero. Basically, that is an error rate of 0% compared to real hardware. It turns out that's very hard. It's amazing, right? You cannot even make this simulator perfect, even if you have the hardware completely in your hand. In fact, RTL is not, usually RTLs of machines have about an error of 2 to 5% compared to, well, I shouldn't say 2 to 5%, it could be lower, of course, but let's say 0 to 3%. It could be 5% if you're not good, but let's say 0 to 3% compared to real implementations. Why? Because there is going from RTL to real implementation, there's a step. Right? And the step involves, if you go through a compiler, the step involves the decisions made by the compiler. Those decisions may be different from what you simulate. Also, if the step goes through a designer, the designer puts some custom logic, maybe even changes what is specified by the RTL, right? As a result, your accuracy is not perfect. But you want to be highly accurate if this is your goal. And there are other goals in between also, actually. For example, you may have explored the design space a little bit, but you want to refine the explored design space without going into a full detailed cycle-accurate design, or gain confidence in your design decisions made by higher-level design space exploration. So these are actually in between these two. And you need different simulators for that. And actually, if you're designing a hardware system, you actually have many levels of simulation. You start with instruction level simulators, and then you go into high-level simulation, a little bit lower level simulator, a little bit lower level, and then RTL. I don't think there's anything below RTL, but that's the real hardware after that. And then you try to validate, calibrate. Okay, so let's talk about trade-offs a little bit. There are 3 key metrics to evaluate a simulator. One is speed, the other is flexibility, and the other is accuracy. And all of these are important, and usually you can get 2 out of the 3 very well. This is one of those things where you can get 2 out of the 3, but not 3 out of the 3. And speed and flexibility clearly enable you to explore fast, right? You really want both of them. Maybe you don't care as much about accuracy. So depending on your goal, you need to really set the standard, set the goals for each of these three. So speed is how fast the simulator runs. There could be multiple ways of measuring it, like X instructions per second, X cycles per second, or slowdown compared to a real system, if you're trying to match a real system that can do what your simulator can do. Flexibility is how quickly can you modify the simulator to evaluate different algorithms and design choices. This is really important, actually. If you're doing design space exploration, this matters, because you may have a very detailed simulator, and that could take you years to change it. It may be actually faster to build real hardware before you change simulator, because there are so many bugs in the simulator. And this is actually a bit dangerous, I think, because a lot of companies have these really sophisticated simulators, and one of the reasons they, in my opinion, they're conservative in pushing big ideas is because they really are slaves of the simulator. Because they go into the simulator, they change something, and the idea may look really nice, but then once you go and implement in the sophisticated simulator, they need to fix a lot of these different parts that also need to change. And that takes so much time that people get disillusioned and they abandon the idea. I think this is a real effect of using the wrong level of abstraction in the simulation to evaluate a particular idea. To evaluate a particular idea, I think you need to find the right level of abstraction in simulation. Otherwise, you may never enable that idea. And for that, flexibility is important. Accuracy, clearly, how accurate the performance or energy or whatever numbers the simulator generates are versus a real design. This is a simulation error. Of course, in some cases, this is also important. And the relative importance of these metrics varies depending on where you are in the design process and what your goal is. If you're in the exploration process, speed and flexibility are very important. Accuracy may not be as important. If you're in the debugging process after you finish the hardware, accuracy is extremely important. Maybe you don't care as much about flexibility and speed. So you really need to figure out where you are in the exploration process. In research, for example, usually flexibility and speed are very important, because in research, your goal is really not to debug the hardware in this case, right? And if you really want to change the paradigm, I think you need just enough accuracy, and you need to be speedy and flexible. Okay, so this all is a trade-off, right? Speed and flexibility affect how quickly you can make design trade-offs. Accuracy affects how good your design trade-offs may end up being. So this is still important, accuracy. You cannot give up accuracy completely, right? Otherwise, you basically have pipe dreams that are useless. Also, accuracy affects how fast you can build your simulator. There are two interesting things over here. Simulator design time. That's another metric. I didn't put it as a first-class metric. This is a second-class metric that's also important, that affects how fast you can explore things. Flexibility also affects how much human effort you need to spend modifying the simulator, actually. And I know of simulators that can actually break projects. And I will not name companies, but there was this big project in a company, and people built a simulator that nobody could modify, and they were almost abandoning the project. And some people actually rewrote the simulator from scratch, and that enabled that project to be successful. And you're using a lot of those processors. Well, if you're older, you were using a lot of those processors, actually. Okay, so essentially, these are important issues. Basically, you could potentially destroy a project if your simulator is not good enough. And you can trade off between the three to achieve design, exploration, and decision goals. So high-level simulation, I'll go through this quickly because I think they're going to go inside, but I think I'm going to keep them out for a while. So basically, the key idea in high-level simulation is to raise the abstraction level of modeling to give up some accuracy to enable speed and flexibility. So it's a conscious design decision that you're making. And you're also enabling quick simulator design. And I think this is very important for research. And of course, with everything else in the world, there are advantages and disadvantages. Advantage, you can still make the right trade-offs and can do it quickly. Of course, you need to be careful in this. That's why this is an art, an experience. Experience is very important. That's why it's good to play with simulators a lot. But of course, how do you get to this advantage? You need the modeling of key high-level factors. You can omit corner case conditions. But you should always check these corner case conditions in your simulator. For example, you're not modeling something. I don't know, let's say a page fault. You're not modeling page faults. Let's assume that. That may not be a good idea. But you're not modeling page faults. If page faults are not happening, you're OK, right? But how do you know whether page faults are happening or not? Well, you add a counter. You somehow have checks in the simulator saying, oh, I think a page fault may be happening here. I'm not modeling them, but I'm going to count them. And if that counter is a lot, then you probably were doing the wrong design choice in not modeling them. Right? That's the idea, basically. You add these enough checks when you're not modeling something. But you can get away without modeling a lot. And also, all you need to get correct is the relative trends, not exact performance numbers. That's what we're looking for here. Of course, disadvantage is if you don't do things right, you open up the possibility of potentially wrong decisions, right? You may think processing in memory is the best thing in the world, but it's useless. I don't believe that, but it's possible, right? So basically, how do you ensure you get the relative trends accurately? You design your simulator well, and you ensure that you're not omitting things that are really important. And also, I mean, this comes a little bit with experience also, I should say. I think simulation is a progressive refinement also. That's another way of simulation. Basically, you start with very high level models that are abstract. Analytical modeling actually sits on top of this. And then you move into simulation potentially. And then you have less abstract models, and then you have low level models, and then you have the real design. And as I said, as you go down, as you refine, abstraction level reduces. Accuracy hopefully increases, but not necessarily if you're not careful. I've seen examples where simple analytical models are better than high-level models because high-level models are not capturing everything, but analytical models may be capturing something, especially energy models, actually. And flexibility clearly reduces as you go from top to bottom. Speed also likely reduces, except for real design. Of course, real design is very fast in executing your program, but it doesn't allow you to change things. And of course, you can loop back and fix higher level models, right? So if you have this infrastructure, which is really good to have, you can loop back and fix some of the issues that you may have earlier. And that's the advantage of a company that has been doing this design many, many years. They have many, many of these simulators, and they can loop back and change. But of course, sometimes they get caught up in modifying the wrong simulator for a different idea, right? So that's really important to pick which simulation model you're going to use for an idea. In general, as I said, if you're tweaking things, it's good to do this part. But if you have a big idea that's supposed to change a lot in the system, you probably want to scrap this one and not look at it, and you start with the high-level model again and build down. Okay, so making the best of architecture, in my opinion, I think a good architect is comfortable at all levels of refinement, including the real design. I know it's a lot. It takes time. Including the extremes, that's analytical modeling and the real design. And I think it's really important when to use what type of simulation, as I mentioned, right? If you don't do that, then you may actually dismiss an idea that's good, or you may actually enable an idea that's useless, or that may not be good. And as I said, there are a variety of evaluation methods that are available. And I said simulation is one of them. But if you can do theoretical proofs, that's good. If you can do analytical modeling, that requires its own short lecture, probably. That's also good. And prototyping, that's also good. So I think it's good to be good at everything. Of course, I think this is a bit difficult in architecture in general. It requires a different mindset also. How many of you are theory folks here? How many of you enjoy theoretical proofs? Okay, so you may change this also. So there was a time where computer architecture was actually very theoretical earlier in 1950s, 1960s. A lot of the caching mechanisms were developed with some theory. I mean, I don't think they ever proved anything as much. You can prove some things, of course, under some conditions with restrictive conditions, but workloads are so various that they exercise many, many conditions. They basically almost always violate those assumptions. So I think it's good to think about how to do these in architecture going forward, but it may not be very easy. Okay, with that, I'll introduce the Ramulator in the -2 minutes we have. But basically, we release a lot of simulators, and I think this is one. If you're interested in memory system research, you should definitely start with this one. We were not very happy with all of the memory system simulators. That's why we started with this one. Actually, this is the 10th year iteration of the simulator that I started developing at Microsoft Research. Not the 10th year. Yeah, 2006, 2015, that's 10 years, right? Okay. So it evolved over time. And it basically is this. Essentially, our motivation was the DRAM and memory control landscape is changing. There are many new and upcoming standards and many new controller designs. We wanted a fast and easy to extend simulator that can enable you to look at these many different standards. And Ramulator is what we came up with. It was released in 2015. It provides out-of-the-box support for many DRAM standards, like all of them. And I think there are new ones also. HMC, for example, released a new one. These are different DRAM standards, some of which we talked about, and also some academic proposals. And there are, of course, some open source simulators that we compared to. It's faster than fastest open source simulator. Not all of them are designed to be flexible. Actually, none of them are designed to be flexible. Ramulator was designed to be flexible. It turns out it's also very high speed because of its modularity. So we wanted it to be extensible to different standards. And this is from the Ramulator paper. This is the kind of study that we wanted to be able to enable. I'll do this very quickly, but basically these are workloads across 22 workloads. You can look at the effect of different standards. This basically shows that DDR4 improves performance compared to DDR3. That's not always the case. For these workloads, it happens to be the case. Sub-array level parallelism actually is better. High bandwidth memory is even better for these workloads. Wide I/O reduces performance. LPDDR4 actually reduces performance, as you can see. So you can actually do this all with Ramulator. And this is one of the recommended readings. And I would suggest an optional assignment. You don't have to do it. You can review the Ramulator paper and download and run it. And I think this sort of simulator reduces the barrier to entry to memory system research. It'll help you get into memory system research. And this is the paper that I mentioned that's appearing in Sigmetrics. That's one study that we spent some time on, a couple of years, to understand the interactions of workloads and DRAM types. And I've copied it and pasted it. But basically, we looked at 9 different DRAM types and 115 modern applications and workloads. And we have a bunch of key observations from our study. It's a very empirical study. It's based on Ramulator, a new version of Ramulator that's going to be released with this paper. But let me give you a couple of things that you can find this way. You cannot do this on a real system. There's no real system that supports all of these different standards at the same time, right? As we discussed in memory controllers. It's impossible to build that system. But basically, newer DRAM technologies such as DDR4 and hybrid memory cube often do not outperform older technologies. That's very interesting, due to higher access latencies, and in some cases, poor exploitation of locality. There's no single memory type that can cater to all of the SoC accelerators that we have. For example, graphics DDR significantly outperforms other memories for multimedia, while hybrid memory cube, which is the 3D stacked memory, outperforms other memories for networking. So it really depends on the application, what memory you need. So you cannot have a single SoC that is a memory that's good for all of the applications that's executed on the SoC. And I think this is very important, and this motivates what we're going to talk about next. We knew this before also, but this paper verified it much more strongly. There's still a strong need to lower DRAM latency, but as you saw in the first lecture, unfortunately, the current design trend of commodity DRAM is toward higher latencies. DDR4 actually increases the latency to obtain other benefits like higher bandwidth or lower energy. That's one of the reasons why we're going to talk about latency, because I think that's going to be very important. And we recently released Ramulator for PIM, and this is the DAC paper that has released it. And I think this is a good place to stop, because otherwise they may invade where we are. What do you think? So please hold your questions for tomorrow, or feel free to email me, unless you have a burning question that may risk the invasion of this room. We do? No questions. Okay, I'll see you tomorrow then. Thanks. Slides are actually already on the website.